Okay, so a carboxylic acid and ester are similar groups. A carboxylic acid is a little bit easier to recognize and name because the carboxyl group, which is this functional group here, is found at the end of the chain always. And these molecules are the most reactive and of all the organic molecules, and also the ones that as humans we make use of them as well. So like vinegar is acetic acid, or ethanoic acid. Formic acid is the acid secreted by fire ants, that kind of thing that you feel the burn from. So they are always given the number one spot in an organic molecule, similar to an aldehyde. So in a real world, you would never have an aldehyde at one end and a carboxylic acid at the other. Like, you would always have one or the other. You would never have both. So then in a carboxylic acid, the carboxyl group is always at the end. Whereas esters is not like that. They're a little bit trickier. So let's do the easy one first. So you're going to count the longest chain, as always. And then the ending we're going to use is oic acid. You can have acids at both ends, called a dioic acid, but again, that's very rare. Okay, so propanoic acid, it doesn't matter if you prefer one end over the other. Draw your 3, draw the C double bond O and OH at the end. We can do a di one. Let's do pentadioic acid. But again, they have to be at the end. So you just draw the 5 carbons, 1, 2, 3, 4, 5, and that's it. Don't have to worry about numbers or anything like that. Okay, so methanoic acid is only 1 carbon. So this 1, 2, 3, 4 is butanoic acid. And butanoic acid smells so bad that if I opened a bottle in the school, the entire bottom floor of the school would smell like vomit. So these are pretty pungent odors. Even vinegar, right? It definitely has, it's distinctive odors, right? Definitely has a strange smell. So a unique characteristic. Octanoic, 1, 2, 3, 4, 5, 6, 7, 8. Squeeze it in there. I'm going to put mine at this end this time. Okay, easy peasy. So another reason why these are considered to be, important, so to speak, they have OH and they have C double bond O. Okay, so the OH can form hydrogen bonds in 2 ways with other, I'm going to put themselves, so like with other acids and with water. And then the C double bond O can form H bonds with water. So now you've got all these places for these molecules to interact with water, to interact with other molecules. So they will, similar to other acids, they're water loving, they dissolve in water. Okay, so they make stronger hydrogen bonds because they have this extra spot that they can do that. Now, the solubility in water will decrease as the number of carbons increases, as we've been seeing. Okay, so the only reaction they're going to do the reaction to form them is an oxidation. So remember from the aldehydes and ketones lesson, this means an oxidizing agent, and it's simplified. Right? So we are not worried about balancing these. So because an aldehyde has the C double bond O at the end, then when you go to make a carboxylic acid, which is also at the end, the functional group, then now you've got that at the end there. So this is specifically 2 carbons, 1, 2, that's ethanol. So even with an aldehyde, right, we didn't write the number 1, that the double bond O was on the first carbon because it was at the end, and then ethanoic acid. Okay. So now here we have an ester. So its functional group almost looks like a carboxylic acid, except so here we have the functional group, and then here we have carbon chains. So we've used that letter R to represent carbon chains before. So they can be, I guess not chains, a chain. You can they can be the same, they can be different, they can be 1 carbon, they can be 10, it doesn't matter, okay? So the weird thing about this is the name actually has 2 parts, okay? So if you have 2 colors, pick a color. I'm going to change this, sorry. Okay, so the first part of the name is connected to the single O. And then the second part here is connected to the C double bond O. So it doesn't matter, like if you look at the examples drawn here a little bit, so it can be where the ester part is this way, like to the right or to the left. That part doesn't matter. It's more about which one is connected to the single oxygen and which one is connected to the double oxygen. So the one that's connected to the single bonded oxygen, then you just count the number of carbons and add the ending YL. And then the one that's connected to the C double bond O, you count the number of carbons and add the ending anoate. Okay, so let's just do some examples. That's probably easier. So you're looking for the first part goes with the single bonded oxygen, so that's 2 carbons, so ethyl. And then the second part is connected to the C double bond O, but that also is a carbon, right? So you have to count that one as well. So 1, 2, 3, 4, ethyl butanoate. Okay, so connected to the single O, 1, 2, 3, propyl. Including the C and the C double bond O, 1, 2, 3, 4, 5, pentanoate. Connected to the single O, 1, 2, 3, 4, butyl. One, 2, 3, 4. Butanoate, so they can be the same. That's perfectly fine. And this is actually the synthetic smell of banana is butyl butanoate. Okay, so connected to the single O, ethyl. And then this time there's only one, which is methanoate. Okay, so if you want to because we read English left to right, some people will, because the methyl's written first, they draw that first, but it doesn't matter. And then the octanoate part goes with the C double bond O, but that includes that as well. So this counts as 1 carbon, 2, 3, 4, 5, 6, 7, 8. Okay. And then propyl pentanoate. So 1, 2, 3, single O. Pent is 5, 1. Oops, Sorry, that's terrible. Let me do that again. 1, 2, 3, 4, 5. So the big thing with the ester is you have to have the functional group connected to the same carbon, okay? Sort of in the interior of the chain. So I know that I think Mr. Adams, he uses the trick, I guess, that the ester kind of looks like somebody wearing glasses, like an ester and old grandma. I don't know. Whatever helps you remember, okay? And then decal is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh. And 2. Butyl, 1, 2, 3, 4. Sorry about that. Prop, 1, 2, 3. Okay. So again, they are synthetic odors. So we wouldn't have used butanoic acid because it smells like vomit, but we would have used glacial acetic acid. So that's like super concentrated vinegar smelling. Ethanoic acid, even that is a very pungent odor. And we would have tried to make smells. So like oranges, we can make pears, fruity. Sometimes they don't smell great, but we do our best. Okay, so because these molecules get really big really fast, so then they're often less soluble, but they also don't have the extra OH group like carboxylic acids do. And then like I said, usually the smaller ones are gases, but they get big pretty fast and they turn into more like liquidy solids. Okay, so esterification reactions are important, and if you took biology, you would have done these reactions because ester linkage is like a polyester and then the next one we're going to talk about is an amide, like a polyamide or a protein. So when you have, sorry, this is a bit wacky, but you have a carboxylic acid and an alcohol coming together, and oh, what a shocker, you make water, okay? So these can also be called condensation reactions. And when you have the acid and the alcohol coming together, you're going to make HOH. It doesn't really matter which O goes with what, but if you want to keep with what we just did, then we'll say that it keeps this oxygen and gets rid of that hydrogen, and then this group is removed to make water, and then these two come together. So again, if you want to keep with the same colors, this part came from the alcohol and this part came from the acid. Okay, and then you can do the reverse reaction where you split by water into alcohol and carboxylic acid, which is called hydrolysis. So hydro being water and lysis means splitting. Okay, thank you.